Stress analysis in piping system. This episode has been divided into two sections. First section, that is this video, will discuss about the weightage, basics, and the prime component of stress analysis, while the second section continues from where the first section ends and illustrates further the failure theory, forms of loading in piping system, types of analysis, different load cases, the allowable references, and inputs required by the piping engineers for performing stress analysis. So beginning with the first section, I will be discussing out the weightage of stress man-hours and engineering man-hours, what is stress analysis and why stress analysis needed, the change scenario, failure modes of piping system, stress strain curve, loading present in a piping system, and the stresses in pipe. So beginning with engineering man-hours. Out of the total job man-hours provided for a particular project, engineering man-hours constitute roughly around 40 to 48% of it, and piping man-hours constitute about 20 to 25% of the allocated engineering man-hours. That is roughly around 1/5 to 1/4 of the allocated engineering man-hours. Stress analysis man-hours is confined to 8 to 12% of the total piping man-hours. So though stress analysis constitutes a rather insignificant amount of total job man-hours, piping being the most delicate component in any process plant and also the business entity are subject to almost all kinds of loads. Ignoring or misreading any such loads while designing, erecting, hydrotesting, startup, shutdown, normal operation and maintenance, etc. can lead to inadequate design and engineering of a piping system. The system may fail at the first occurrence of the overlooked load. Failure of a piping system may trigger domino effect and cause a major disaster. So it is very important to take note of all potential loads that the piping system may encounter. What is stress analysis and why is stress analysis needed? Why we perform this stress analysis? Now, before understanding what is stress analysis, let us see the prime objectives of the piping design. We design piping system which is economical and works satisfactorily. That is, it will perform the intended service for the intended time and not fail and will not put excessive loads on other equipment or the structure. So finally, we design a piping system. What is it intended to finalize? Pipe. Piping design is first of all intended to finalize the routings, and these routings are sometimes governed by P&ID notes and requirements which needs to be taken care of. Again, the availability or the possibility of the structural member, and the routings are made so that it takes care the excessive thermal expansion. In piping design is meant to finalize the supporting, and this supporting should take care of the excess weight and pressure in the piping system. The PSV arrangements, the supporting should be done so that the PSV should function properly. Supporting should be done in order to take the occasional winds and seismic loads, and if the piping system is having a two-phase surge line, then the proper supporting is required. Again, this piping design is finalized based on the loadings that needs to be provided at the terminal points, like that of heater, the anchor bay, the battery limits and the supports, or the loads on the equipment nozzle to which it is connected to. The loads to the structure are the support members. So, in a nutshell, piping design is required to finalize routing, supporting, and loads on the terminal points, equipment nozzles, and supporting structures. These factors which we saw are mostly weight governed, force governed, load governed, and expansion governed. So these are the factors which determine the routing, supporting, and the loads on the terminal points of the equipment nozzles. Thus, we need some method to get these details in order to obtain a safe piping design with the help of knowledge acquired in the form of educational qualification in subjects like mechanics, strength of materials, solid mechanics, finite element analysis. One is able to determine these governing parameters and associate them with the relevant factors involved. Also, all these governing parameters are calculated and related with the practice and experience coupled with theory and experimental data. The process of determining, associating, and analyzing the factors discussed are called stress analysis, and this can be achieved by general layout design, rule of thumb, nomograph, charts, and various related softwares. For different industries and service requirements like power industry and power piping, process industry and process piping, pipelines, there exists simplified practical methodology of implementing knowledge which assists in achieving acceptable reliability in the form of governing codes like B31.3, B31.1, and 31.4, etc. This, with the proper blend of knowledge, codes, and tools, the requirements to meet the very objective of piping design is met. In a nutshell, areas in piping stress analysis lies in the domain layer of knowledge, comprising of theory, experimental data, experience, practice, and the subjects that is being studied. Codes, which is simplified practical methodology of implementing the knowledge to achieve the acceptable reliability, like ASME 31.3 for process piping, and tools to implement the methodology in reality, the general layout, rule of thumb, nomographs, charts, and softwares like Caesar. And encompassing these three domains, stress analysis tries to meet the objective of piping design and thereby leading to a better working plan. Earlier, before the advent of computers and advanced computing softwares, pipe stress analysis was handled by very specialized engineers. Based on subject knowledge and code guidelines, it normally took a specialist to use a calculator and work out the formula results to analyze the flexibility of moderately complex piping system to absorb the thermal expansion of the pipe. With the rapid advancement of computer technology and software, calculations became easier and faster. Suddenly everybody knew how to analyze pipe stress. The task of stress engineers got shifted from the traditional calculation of stresses to stress engineering. The emphasis is not on how to calculate the stress, but rather on how to utilize the analysis tool to design a better plan. So this is how the mode changed. First, the traditional stress calculation was done, but nowadays stress engineering is done in order to build up a good and a better plant. However, just because it is easy to get the stress calculated, engineers often depend too much on the computer and forget about the fundamentals and engineering common sense. The cone got overturned. Software charts and nomographs has become the top priority. Due to this overdependency and electronic adaptation, and without much fundamentals and common sense, one may not be even aware of the unreasonable results produced by the computer. As we discussed, a piping system must be designed so that it works satisfactorily without failure. Now, what is this failure and how can a pipe fail? A piping system may Under C, any of the four failure modes described below. It may fail in strength, that's yielding by yielding or by rupture. Piping will fail in fatigue. It may fail in creep at a high temperature, or by buckling, that is called the stability failure. And there are other miscellaneous modes of failure like corrosion, erosion, and sagging, excessive sagging. So these are the failure modes in which a piping system will fail. Fracture or catastrophic failure due to pressure has been elaborately discussed in previously uploaded video titled Wall Thickness Calculation. So one may go to this video. The rest has been elaborated in this video. Failure by yielding rupture. For brittle material, strict control of stress and nature of loading is required. In places where mechanical or thermal shock loadings are anticipated, they cannot be used as these failure occurs unexpectedly and suddenly. This is due to the brittle material's low energy absorbing capacity, where even a slight impact or deformation translates to a higher stresses. And to these materials, the high stresses which is developed can only be relieved by yielding. So it just yields at the very onset of the impact loading. In case of ductile materials, as the loading increases or when impact loading is done, the material is capable of absorbing excess energy by undergoing considerable plastic deformation and fails after going through fairly large amount of elongation. They elongate to about 25% before failure. It also redistributes the high concentrated stresses into a more favorable stress distribution during yielding. So herein, because if the loading is done, either it be impact or gradual loading, it yields by absorbing energy, and thus the sudden failure is not present. Now let us look at the stress strain curve for various different materials. A brittle material has a linear stress versus strain curve, and here we can see from a very small stress considerable amount of stress is produced. So the failure of a brittle material is sudden and with very little or no plastic deformation at all. For a reasonably strong material than that of the brittle material, but however not ductile like that of a steel wire, which stretches very little and snaps, that is breaks suddenly, we have a linear stress versus strain graph, and it shows that we can have a considerable amount of strain and the stress is distributed, but again it snaps suddenly. For a ductile material, after the elastic region, that is the rectilinear portion wherein the stress is proportional to the strain, a strain section called necking occurs, wherein permanent deformation starts taking place and the material enters into a plastic region zone. So here the rectilinear behavior is there between the stress and the strain up to a particular limit called the yield point, and then on further increase of the stress, strain increases considerably, leading to a plastic deformation, and then there is a increase in stresses accordingly. For a plastic material, we see that it's a very small elastic region, and the strain we can strain out the plastic material without getting higher or the larger magnitude of stress developed within the material itself. So they can be elongated to a larger extent. So this was the strain curve for the various materials. and various materials how they yield. Some snap suddenly, and some are capable of giving indications by providing necking, and some materials like plastic materials which can be deformed to a larger magnitude to absorb the stresses, to absorb the energy and the residual stresses to be given out. There are some materials which becomes brittle due to temperature changes. Most piping materials lose their ductility as the temperature drops below a certain limit. Also, there are few materials that become brittle at high temperature due to the metallurgical changes. So here we see as the temperature increases, the ductility behavior also increases. That is, when we go down the line in the temperature, the energy absorbing capacity of a material decreases and the material is tend to become brittle. And this is true for the carbon steel, wherein the material which itself is a ductile becomes brittle below a particular temperature. In some materials, this behavior is shown at an elevated temperature. That is, when we have a higher temperature, the material turns brittle again. These losses of ductility is a serious concern to piping, and process piping code sets a very detailed role and requirement on materials at these temperature changes. Now, fatigue failure, that is the second mode of the failure. Thermal or mechanical fatigue is usually the most common cause of failures in high temperature cyclic piping systems. Thermal fatigue is caused by frequent change in operating temperature. Mechanical fatigue is caused by pipe movement, vibration, restraints preventing free movements, and other conditions. Again, there are systems where loading cycles are in millions, like rotatory machinery, centrifugal and reciprocating, centrifugal compressors, reciprocating compressors, the pumps. Herein, they are the rotating machinery with the rotating parts attached, and these undergoes large cyclic loadings. Fatigue in these systems can be classified as a high cycle fatigue. In piping systems, the loading cycle applied are frequently only in thousands and sometimes in hundreds only, and mainly they are in the startup case or the shutdown case and regeneration cycle cases. So these type of fatigue are called the low cycle fatigues. So we have a high cycle fatigue and a low cycle fatigue. In both the cases, due to the cyclic nature of the loadings, piping fail under a stress much lower than the ultimate strength of the material. Next is the creep failure. At high temperatures environment, piping continue to deform under a sustained, that is weight and pressure loading. The pipe may fail after a certain period even if the stress is much lower than the ultimate strength of the material. This time-dependent progressive deformation and consequent failure is called the creep. Creep occurs only at high temperatures. Next we have stability failure or the buckling, generally occurring in a thin walled cylinder or thin walled pipe or the excessive where there is excessive pressure. Stability failure is mainly caused by the compressive stress. This failure mode is prone to large thin walled shells and pipes. Also in thick pipes, these failure modes may occur, but only when subjected to a high external pressure like deep water. There are some other failure modes like corrosion, the corrosion, erosion, and hydrogen attack. Corrosion basically affects the piping in two areas. First, there is a reduction in the wall thickness, and then there is a stress intensification of the wall corroded pits. These corroded pits can greatly reduce the fatigue strength of the pipe under cyclic loading. Rubbing of flowing fluid against the pipe wall erodes the pipe wall to some extent and Most two-phase flow cause significant erosion. Turbulence, the low pH and low oxygen content are some other parameters that favors erosion of carbon steel pipes. And then we have the excessive deflection or sagging, which is caused in the piping system leading to the fluid trapping, and generally in the condensate systems this becomes a serious concern. Next we will be seeing about the stresses in the pipe. As discussed previously, pipe is subjected to various kinds of loads which needs to be identified. Each of such loads would induce in a pipe wall normal and shear stresses. So normal and shear stresses are induced in the pipe wall due to the external loadings. These normal and shear stresses needs to be calculated from the standard relations, and then we arrive at a net normal and shear stresses. Once net normal and shear stresses are determined, principal and maximum shear stresses is calculated. So our aim is to calculate the principal and the maximum shear stresses within a piping. Some basic potential load forms faced by the pipe which results in these normal and shear stresses are summarized in brief. We have internal and external pressure loading, which leads to longitudinal pressure stress, hoop stress, and the radial stresses illustrated in the earlier uploaded video. Forces leading to the axial stresses and the shear forces. The forces, the axial and the shear forces, they leads to the stresses in the piping system and the components. And the load form is in the form of moments, wherein we have a bending moment and the torsional moment causing the stresses. Stress categories. We have three stress categories. First is the primary stresses, secondary stresses, and finally the peak stresses. Primary stresses are developed by imposed loading and are necessary to satisfy the equilibrium between the external and internal forces and moments of a piping system. These are not self-limiting, that is, these stresses are not cyclic, and the mode of failure is by plastic deformation, gross plastic deformation. Thus, if a primary stress exceeds the yield strength of a material through the entire cross section of the piping, then failure can only be prevented by strain hardening. Next is the secondary stress. Secondary stresses are developed by the constraint or the displacement of the structural system. These can be caused either by the thermal expansion or by anchor point movement. Under these type of loadings, that is the strain governed loadings, the piping system must satisfy an imposed strain pattern rather than an equilibrium with the imposed forces. Local yielding and minor distortion of the piping system tend to relieve these stresses, thus they are called the self-limiting. Most of these are cyclic, and the mode of the failure is by ratcheting or fatigue. So in seconding stresses basically which are self-limiting, herein the piping system satisfy an imposed stress pattern rather than the equilibrium with the imposed forces, and herein what happens is local yielding and the minor distortion tends to relieve these stresses. For these stresses, the allowable stresses are given in terms of calculated elastic stress range, and this stress range can be as high as twice of the yield stress. The reason being, respectively, the repetitively applied loads which initially stress the piping into the plastic yielding after a few cycles which take it down to the elastic action. Next we have the peak stress. The loading condition of the peak stress causes no distortion significantly. These are highest stress in a region under consideration and are responsible for causing fatigue failure. Common types are stresses due to the stress concentration at the discontinuity and the thermal gradient through a pipe wall. So these are basically the localized stresses present in the entire system, which are peak, and again they are cyclic in nature. So this ends up with the first part of this section. In the second section, that is the second part of the video, we will further continue to see what are the various theories of failure, how the loading is present in the piping system, what are the methods to increase the flexibility within the piping system, and what if can happen if we go on continuously to increase the flexibility, what are the various aspects which leads to the design of a span, various types of piping, various types of analysis and the load cases, and we will see to some extent the allowable loads on the equipment nozzles, how they are, from which code they are determined, and piping systems should meet these allowables, and finally what are the various inputs which a piping stress engineer needs to perform the piping stress analysis. So this ends up with the first section of the piping stress analysis.